Welcome back to the deep dive. Usually when we talk about computer bugs, we're complaining. My screen froze or the app crashed.
Or why is the printer making that demon noise?
Exactly. It's annoying, but it's passive. The computer just stopped working.
Right, it's a failure of function.
Yeah. But today is different. We're looking at a stack of notes on something called execution flow corruption. And honestly, this doesn't feel like a bug. It feels more like mind control.
That's a dramatic way to put it.
We aren't talking about breaking a program. We're talking about hijacking its brain and forcing it to do things the original programmer, never intended.
Okay, when you frame it that way, you aren't actually that far off. We're looking at vulnerabilities that let an attacker essentially rewrite the reality of a program in real time.
We have some pretty dense technical material today, specifically a breakdown of Stack Overflow execution flow. And we're going to tear apart two examples, authenticate3.cpp and so staito.cpp.
Yeah.
But before we dive in, what's the mission here? We aren't just crashing systems for fun, are we?
No. Well, I mean, crashing is sometimes a side effect, but the mission is control. The sources describe this as a violation of the program's integrity. Think of it like a train on a track. It leaves the station. It's supposed to go to stop A, then stop B.
Okay.
Execution flow corruption is like someone walking up to the switch track, pulling the lever, and sending that train down a completely different track, one that wasn't on the map.
A track that maybe leads to a vault.
Exactly, or the conductor's cabin. The point is, you are now driving the train, not the system.
I love that image.
Yeah.
But to pull that lever, we have to understand how the tracks are laid out. The source material spends a lot of time on the stack. Now, when I hear stack, I think pancakes. Is that too simple?
No, actually pancakes. That's a great analogy.
Yeah?
Yeah, because in computer science, a stack works on a principle called LIFO, last in, first out. If you have a stack of 5 pancakes, you can't just eat the bottom one first. You have to take the top one.
Unless you're a monster and just cut down the middle.
We'll assume standard pancake etiquette. So in a program, this stack is used to manage memory for functions. Let's say your main program is running, we'll call it the caller.
Okay, the caller.
And it needs to do a side task, like checking a password. So it calls a function.
That's the Cali.
Right. Now, the program has to pause what it's doing and jump over to that password function. But here's the critical part. It needs to know where to come back to when it's done.
It needs a breadcrumb trail.
A breadcrumb trail, exactly. So before it jumps, the caller takes a specific address in memory, the return address, and pushes it onto the stack. It's like putting a bookmark in a book before you go check the glossary.
Okay, so the return address is the bookmark.
Mm-hmm.
And it's just sitting there on the stack.
Yes, and here is where the pancake thing gets really important. Once that bookmark is down, the function starts piling its own stuff, like the space for the password you're typing, right on top of that bookmark.
Wait. So the data I'm typing in is sitting physically, well, virtually, on top of the very thing that tells the computer where to go next.
Precisely. And in a healthy program, that's fine. You type your password, the function checks it, the data is cleared, and the computer looks down, finds the bookmark, and goes right back to where it was.
But we aren't here for healthy programs. We're here for the exploit. What happens if I pour too much syrup on the pancakes?
If you pour too much syrup, or in this case, type too much data, it flows down. It overflows the buffer. And because of how the stack is structured, it flows directly over that bookmark.
So I've ruined the bookmark.
You've overwritten it. If you just pour random junk, you smudge the bookmark so it's unreadable. The computer finishes its task, looks for the return address, sees gibberish.
And it crashes.
It panics and crashes. That's a segmentation fault, a seg fault.
Which is annoying, but it's not the mind control we were talking about.
Correct. Mind control happens when you don't just smudge the bookmark, you replace it. You very carefully overwrite the return address with a new address, a valid one that points exactly where you want it to go.
So the computer finishes checking the password, looks down, and instead of the bookmark saying go back to the main menu, it now says go to the vault.
And it goes to the vault. It doesn't question it. It blindly trusts whatever is on the stack.
That is terrifyingly simple in concept.
Yeah.
Okay, let's look at this first case study, authenticate3.cpp. This feels like the hello world of this kind of hack. What's the setup?
It's a classic authentication bypass. The program has a function, check authentication. It asks for a password, stores it in a buffer. But the developer made a fatal mistake. They used Strappy.
Oh, Strappy. I feel like I see that name pop up in every security nightmare. What is it about that one command that's so dangerous?
It's not a villain, it's just incredibly naive. Strappy means string copy. Its only job is to take text from point A and put it in point B, but it has no safety rails. It doesn't check if the text fits.
So it's like a packer who just keeps shoving clothes into his suitcase even after the zipper has burst.
That's a perfect way to put it. If you give Strapi 100 characters, but the destination only holds 10, it just keeps writing the other 90 characters right into the memory next door.
Which is where our bookmark lives.
Yeah.
So the source material says they load this program into a debugger, GDB.
The GNU debugger, it lets you pause the program and look at the memory in real time.
Right, so they load it up. They know the return address is sitting there at a location called EBP +4.
Okay.
What exactly is EBP?
Think of memory like a construction site. EBP is the base pointer. It's like the foreman standing at the bottom of the current function's stack frame saying, everything for this job happens above my head.
It's the anchor point.
It's the anchor. And because of the architecture, the return address, our bookmark, is always sitting right next to that anchor, specifically 4 bytes away. EBP +4. It's just the geometry of it.
Got it. So we know where the target is. Now we just need to hit it. The notes say they started by throwing 100 A's at it. Why the letter A?
It's just visually distinct. In hexadecimal, the letter A is 0 by 41. So if you flood the memory with A's and then look at it, you just see rows and rows of 41, 41, 41, 41. It's really easy to see where your input went.
So you send 100 A's, the buffer overflows, the return address gets overwritten with 0 by 41414141. The program tries to jump there, sees it's not a real place, and crash.
So we've confirmed the vulnerability, we can break it. But now, for the precision, we don't want to just hit the target. We need to know exactly how many bytes it takes to get there.
We need the offset.
Right.
If you just guess, you might only overwrite half the address or you might overshoot it.
Yeah.
It has to be exact.
And the source mentions a really cool tool for this, GDB-PETA, and something called a cyclic pattern. So instead of all A's, it uses chaos.
It's controlled chaos. Instead of GDB-PETA generates a string where every 4-character chunk is unique, like ABAD.
So it creates a unique fingerprint for every single spot in the string. Exactly. You feed this pattern into the program, it crashes. But this time, you look at the crash report and see exactly what value got stuck in the return address. Let's say it was KAC.
You just search for KAC in the pattern and you know exactly how far in it was.
Precisely. The tool even calculates it for you. And for authenticate3.cpp, the magic number was 28.
28 bytes.
28 bytes of junk fills the buffer and walks you right up to the edge of the return address. The very next 4 bytes you send become the new bookmark.
Okay, so we have the distance. Now we need a destination. The notes say they used a tool, K, to look up the address of a function called valid.
K is like a phone book for the program. It lists where every function lives.
Yeah.
And yeah, there's a function called valid that just prints access granted. Normally, you can't get there without a password.
But we found its address in the phone book.
Yeah.
So the final attack is 28 bytes of junk.
Followed immediately by the address of valid.
You send that in.
Yeah.
Strapi copies it all. It overflows. It replaces the return address. The function finishes. The computer checks the new bookmark and bam, access granted.
You're in.
That is so satisfying. It's like you're not picking the lock, you're just teleporting past the door.
That's a great way to put it.
But the notes don't stop there. They basically say, okay, skipping a password is cute. Let's take over the machine. So we move to the second example, query.stdio.cpp. What's the difference here?
The stakes are much higher. In the first example, we just tripped the program. Here, we're going to force the program to spawn a shell.
For anyone listening who doesn't live in a terminal, what's a shell?
It's the command center. If you have a shell, you can issue commands directly to the operating system, read files, delete users, install software, you name it. If I get a shell on your computer, it's my computer now.
Right. Total control.
Yeah.
Now, looking at the code for sawstudio.cpp, I see something weird. There's a function called giveShell. It literally does exactly what we want, but nothing calls it.
It's just sitting there.
Yeah. It's unconnected.
We call that dead code. It happens all the time. Maybe a developer used it for debugging and forgot to remove it. It's there, it's in memory, but there are no official tracks leading to it.
No tracks until we build one.
Exactly. The strategy is the same. Find the overflow, in this case, in a function called bad, calculate the offset, and then overwrite the return address to point to giveShell.
The notes say the offset here is 140 bytes. So 140 bytes of junk than the address. But this is where I got a bit stuck. The address of giveShell is 0 by 80080484s. But the notes say you can't just type that. They start talking about little endian.
Ah, yes. The bane of every beginner hacker.
It sounds like a reference for Gulliver's Travels.
It is. Swift wrote about 2 groups at war over which end of the egg to break. In computing, it's about how numbers are stored. We humans are big endian. If I write 5,000, I put the 5 first. The biggest part is on the left.
Right, left to right.
But this computer architecture by 86 is little endian. It stores the smallest end of the number first. It reads backwards.
So if I want to tell the computer to go to address 08, 04, 84 seats,
You have to reverse the bytes. You have to send in Oshis, then 84, then 04, then 08.
that feels so counterintuitive. Why would they do that?
It's technically more efficient for the processor to do math that way, but for a human writing an exploit, it's a classic tripwire. If you send the address the way you read it, the computer tries to jump to a completely different location and crashes.
So not only do we need the key to the door, we have to put it in the lock upside down.
That's the reality of low-level systems. You have to speak the machine's language, even if it feels backward.
Okay, so we have our offset, 140 bytes, we have our address, and we've reversed it.
Yeah.
But we can't just type these weird bytes on a keyboard. Some of them aren't even characters.
Right. You can't type 0xc on your keyboard. So we have to script it. We write the full payload, the junk, and the reversed address to a file. Let's call it payload.txt.
And we use the cat command to feed that file into the program. But the notes highlight a specific gotcha here. They call it the cat trick.
Oh, yeah. This is probably the single most common frustration for people learning this. You do everything right, you smash the stack, you jump to the shell function, and nothing happens.
It just closed.
The shell opens and closes instantly. It's because of standard input, or STEDIN. When you pipe a file into a program, the computer reads the file. When the file ends, it sends an end of file signal.
Okay.
So the program thinks, okay, the input stream is finished, I guess we're done here. The shell launches, sees the end of file signal, and immediately says, well, guess no one's here, and shuts down.
So you broke into the bank, but the automatic door sensor didn't see you, so it locked you out again.
Perfect analogy.
So what's the fix? The notes show this command.cat payload.program, that little hyphen, what is that dash doing?
That hyphen is magic. It tells the cat command. First, send the contents of the payload file, and then switch over to the keyboard and just keep the line open.
It's the foot in the door.
It is. It keeps the input stream alive. So the payload goes in, the exploit triggers, the shell opens, and because of that hyphen, it stays open waiting for you to type commands.
That is such a tiny detail, but it's the difference between a failure and a full-on hack.
It absolutely is.
Before we wrap, there was one last hurdle mentioned. Linux itself has some defenses, right? Something about bench dropping privileges.
Right. Most modern Linux systems, their default shell is paranoid. If it detects it's being run from a process with mismatched permissions, like in a setuid exploit, it panics and drops its privileges back down to a normal user.
So you do all this work to become an admin, you spawn the shell, and the shell itself just says, whoa, you look suspicious, and demotes you.
Exactly. It's a defense mechanism. The workaround in this demo was to use Zish, the Z shell, which doesn't have that specific paranoia built in.
So it's a constant game of cat and mouse. Attackers find a way in, defenders build a new wall.
Always.
So to recap our journey, we started with a stack of pancakes. We saw how a naive command like stracme can spill syrup all over our bookmark, the return address.
We used a cyclic pattern to find the exact distance to that bookmark.
Learned to speak the machine's backward language, little Indian.
And we used the cat trick to keep the door propped open once we got inside.
It really brings it back to what you said at the start. This isn't about the computer breaking. It's about the computer trusting us too much.
That's the huge takeaway. This whole exploit works because the computer blindly trusts the value on the stack. It doesn't ask, hey, who put this return address here? It just sees an address and goes. It's why memory safety is so critical.
And it leaves me with one final unsettling thought. We used that give shell function code that was just sitting there, unused, waiting for us. It makes you wonder, in the massive software we use every day, how much dead code is just lurking there?
Probably a lot more than we'd like to admit.
How many useful or dangerous functions are just waiting for someone to calculate the right offset and build a track to them? Something to think about.
Indeed.
That's it for this deep dive into execution flow corruption. Thanks for listening, and we'll catch you on the next one.